Okay, we're in business. Okay, at this point, we should be almost folded on our foldable. So while you're waiting for me to take attendance, if you can take a look right here at 1 through 5. I'm going to talk about it in just a second, but you can start reading. It's going to ask you about certain pieces of your foldable, which one has those characteristics. So I'll help you out in a second, but let me take attendance first. Israel. Here. Felix. Here. Edith. Here. Eli. Here. Dahlia. Here. Stephanie. Here. Diego. Here. Jamie Lynn. Sandy. Here. Brandon. Here. Brian. Here. Juan Carlos. Here. Martin. Oh, he's here. Ned. Kennedy. Here. Giselle. Here. Caesar. Here. Gustavo. Here. Lirio. Here. Tyler. Here. Melanie. Here. Lazaro. Here. Jonathan. Here. Messiah. Here. Joanna. Kevin. Here. Ehong. Christina. Here. Johnny. Here. Luis. Here. D'Anthea. Here. Brian. All right. Okay. So this foldable, let me just introduce you to the foldable first, and then I'll kind of talk about what I mean for answering these questions. So you should have hopefully kind of started reading over. This foldable, in previous years, has been kind of something that we worked on like as a task where we took functions that we call parent functions that we've seen before, and we recorded a bunch of the things we've talked about this year, like the end behavior of the function, when it's increasing or decreasing, the domain and range, all of that. For y'all, because we lost so many days, I went ahead and I just filled it out to kind of like cut out the day where we were doing the foldable. So right now we're just going to do an activity where you guys are going to kind of like scavenger hunt, look through the foldable. Not like around the room, it's not that exciting, sorry, it should be a scavenger hunt. But you're going to look around the foldable, really excited, and you're going to figure out which function has a characteristic, okay? So for example, I could say, find a function that has a range of 0 to infinity. And you like look right here, and I'm like, oh, okay. A parabola, a quadratic, goes from 0 to infinity. Its range is 0 to infinity, and I see that right here. And if I fold this little flap, what do we call that function? Fold that flap. What's that function called? Anyone? Any takers? A quadratic function. So you could write down quadratic function for that characteristic. Okay? So take a look back at your list. Woo! And I'm going to give you 4 minutes to do as many of these you can, find as many as you can. For the first one, I changed it. There's actually only 2, so I don't want you to be looking forever for the third one. Find 2 functions that have a domain and a range of all real numbers. Okay, and write down the names. Okay, 4 minutes. You can work with your neighbors. Try to come up with as many of these as you can so that you can look around your foldable and get to know it. I thought it was earlier, but then Tyler didn't start. What's that line from? All right, nice. Kevin's got the 2 functions that have that domain and range. Yeah, page 35 in your from yesterday. Yeah. Lovely. For number 2, it might not be perfect. You might not be able to find like increasing that exact interval, but think about negative infinity to 0 is this side of your graph, so you're looking for any functions that side of the graph is increasing. Just 2 for the first one. No, that. In my first class, I didn't realize the mistake, and everyone literally spent like the whole 5 minutes looking for the third one. So for the second one, it means from negative infinity to 0. So this side of the graph, you're looking for functions that this side of the graph is doing what? Increasing. So look for graphs that have that side of the graph going up on cluster versus going down here. How are we doing? How are we doing?
I'm great.
Uh-oh. Uh-oh. Oh no. Oh no. Okay, number one. Domain and range. You're looking at all these of all real numbers, which is negative infinity to infinity.
Because this,
Any that have
that's
negative
what it never gets
for the domain and for the range. This one?
No,
That one has it for, oh, that's, oh.
it doesn't get, like that's one, like you never get to see it, if you close one, then like.
Time check, you got 1 minute, 40 seconds. Do as many as you can. Okay, for this one, I had a lot of people saying that. But notice this one is increasing never. Because if I were to write this like roller coaster, it's going down, to even on the So thinking about from zeros, or sorry, negative infinity to 0 is this side of our graph, right? Negative infinity to 0. You're looking for a graph that this side, in general, we're going up in some way or increasing. Okay. Okay, so look at my picture right here. From negative infinity to 0 is that side of your graph. So you're looking at this side of all the graphs, and you want to make sure that if you're riding in like a roller coaster, you're going up and
You
not
have to say
going
that
down.
it stops and goes.
It's going up, it's
Plus,
increasing.
we can also
Yeah,
see.
that would work. Okay. From negative infinity to 0, that's where I showed you negative infinity to 0, right? So that side of your graph, looking at this side of all of the pictures, should be increasing or going up. I think the reciprocal is going still down. Right, because this is the domain range, we're not increasing, see how it's with increasing, right? This graph is not increasing. Find a graph that you're going up on that side of the graph. Okay, I don't have my clock in front of you, but you should probably be running out of time soon-ish. I knew it was coming. Thank you. All right.
The absolute is also.
Let's take a look. Okay, lots of stamps coming your way. First up. First up, domain and range of all real numbers. There's 2 of them out there. What are they? You looked around, scavenger hunt. Kevin? Identity and cubic function are correct. If you look at the domain and range, they are negative infinity to infinity for both the domain and the range. All right, which function's increasing from negative infinity to 0? That's this side of your graph. Negative infinity to 0. You're looking for a graph that is going up rather than down on that side of the coordinate grid. Jonathan, what did you find?
Cubic and identity.
Cubic and identity again. Because the identity, yes, it's increasing everywhere, but that means it's increasing on that side, right? And cubic, same thing. It's increasing everywhere, but that means it's increasing on that side at least. Okay? Alright. Next, what does it mean for f of x to be greater than 0, just for anyone that was confused by that before we look for a graph? What do I mean by f of x greater than 0, Ehan? The letter? Y is greater than 0. So we're thinking about graphs that literally only have points up there. They shouldn't ever be down in the negatives for y. So look at your graphs. Even if you didn't get to this one yet, you can still get participation points. What do you think, Brian? Square root, I agree. Look at the square root function. It's like that little blink, and it's above the x-axis, so that's positive. Another one. More hands, more hands. Find another one. Joanna. The quadratic. Yep, it's like the U that's up there above, Sandy. The constant. Okay, this one is kind of debatable, but I'm going to go with it. The example that you see on your foldable, I agree, is like this, right? So it's above. However, that represents any C value, right? Like it's just saying like a constant line. So C technically, if I drew it another way, could be a negative number, and then like all of them would be below. So I'll give like halvesies. You can write that one on there for our example, but I want you to know it could be negative as well. Diego?
The absolute value.
Absolute value, right? It's up here as well. Are there any others? I think we got them all. Quadratic, square root, and absolute value, and kind of the constant, depending. It could all be above or it could all be below. Okay. Oh, Kennedy.
So is it greater than or equal to, or just greater than?
Spice.
Spice.
That's 2.
Great
Azra.
thought. You got me.
So,
Ooh.
all of them are touching 0. So it's all or nothing. Either you're being like me and you just like assumed it was like above or 0, which technically I agree, Kennedy, means it would have to have that equal sign, right? And then all 3 of these would be your answer. If you're Kennedy and you're like really paying attention to things and you're like greater but not equal, then like all of these are eliminated because they all have the point 0, 0, right? And then you would say none. So extra points. 2 stands for you. All right. Next. Which stop? Stop 2. 2 stops on 2. 1, 2. That's like 3. Sorry. Anyways, I'm delusional. Okay. Next one. End behavior. Your left and right limit. Both of them are like this, going up. So which ones look like that? Deanthea.
Absolute value.
Absolute value, there's one of them. Anyone else? Joanna? The quadratic as well. They both are going towards infinity on the left and the right. Okay. Last one. On the right, it's going to infinity. The first one's the right. Right, it's going to infinity. Left, it's going to negative infinity. Looks like this. Find them. Find them. Tyler.
Identity function.
Identity function is correct. Another one. Yep. The cubic function as well, and I believe that's it. Scavenger hunt is over. All right. Cool? So this is your foldable. You get to keep it. You can look up your parent functions. You do not need to like memorize all of this information, but you should be familiar or able to figure out where it's increasing or decreasing, kind of like you had to do in this activity. On your problem set, there's like 3 or 4 more of these statements where you need to pick and choose. So bring your foldable with you wherever you're completing your problem set, and you can look things up. Okay? Today, we're going to be taking these parent functions, they're like the parents, and we're going to be looking at like the next generation, which is like similar, right? Like you're maybe kind of like your parents, but then you're different. So we're going to talk about taking these parent functions and doing transformations. Which, what does it mean in like the English language to transform something? To change, right? So like transformers like change into these robot things. So we're going to take our graph of a quadratic and change it up and move it around on our graph and make it skinnier or wider. And that's going to be what we call a transformation. So let's take a look. Before we jump to your table there where we're going to kind of like record when this happens like more formally, I had an activity originally planned where we were all going to be on our calculators like changing things and seeing how it changed. But to save us some time from the days we lost, I'm going to kind of just show you the graphs, and I want you guys to come up with observations for us to explore this before we write down our definitions. So let's take a look at the first one. And I believe some of y'all have probably done this before, so you can use your previous knowledge or just your observations. So take a look. This isn't in your notes. Here is a quadratic, our parent function, the original. Here I have changed it slightly by taking x squared and adding 2. Raise your hand if you can tell me, in your own words, what happened to our original function when we just added on that 2? Melanie?
The plus 2 is the y-intercept.
Oh.
So you put you add 2, so the quadratic function went up 2.
Up 2. It went up 2. Okay, so using that, if it went up 2, which some of you all have probably seen this, if I were to have one that looks like this, let's mix it up. If I have now the, what do we call this guy? Absolute value function. If I take the absolute value function, but I tack on a -3 to the end, raise your hand if you can use what Melly just said and tell me where this guy is gonna, or how it's gonna change. Lirio?
Going down 3.
Down 3. So it'll look like this and go down 3 down here. Okay? That is what we call this is a type of transformation that we call a translation, or you also might hear it referred to as a shift, like you shift up or you shift down. Raise your hand if you've heard these things before. Okay, hands down. When you translate something from English to Spanish, right, it should have the same meaning, like it still looks like the same absolute value, it's just looks a little different, it's moved down or moved up. Okay, that's when you're adding or subtracting, and we noticed adding or subtracting on the outside because next one up, we got our cubic, okay, cubic function. This time I'm adding 2, but it's a little different than last time. This time, where am I adding the 2? What's different about adding 2 this time, Ihong? It's inside the parentheses. So I'm adding and subtracting, but I'm not doing x cubed plus 2 like that. I'm doing x plus 2 cubed. It's the inside. And so it didn't go up 2. Where did it go? This is your chance, people. Eli, what's up? Where'd it go? It went to the left 2. That's kind of weird. Anyone think, yeah, that's weird because earlier, plus 2 going up 2 makes you feel good, right? Plus 2 going back 2, you got to think it's kind of like the opposite of what you would think. A lot of students would think plus 2 would maybe move them forward 2. Plus 2 is going to go back 2. So while I go bring Lirio her stamp, let's look at the next one. If this is your function, if this is the square root function, and I want to subtract 1 on the inside, it's not going to go down 1. Where is this function going to move? I'm going to do a translation. Christina, where?
To the side.
To the side. And let's think, if this one went back 2 when we added 2, Christina, if this is subtracting 1, is it going to go forward 1 or back 1? Forward 1. It's kind of like the opposite of what you think it'd go forward 1. Okay? Alright, so that's all of our adding and subtracting. You're either going up or down, or you're going left and right. If I add or subtract on the outside, I'm going up or down. If I add or subtract on the inside, I'm going left or right. Okay? Next up, we're not adding 2. Now we're multiplying times 2. What do you observe about our graph, Sandy? Yeah, okay, so it got, there's a lot of words to describe this. Oh man, y'all are I'll tell you all the words.
Consumió Herbalife.
Yes. Man, I heard them cheer for you earlier. Great job, by the way. I meant to tell you. That was inspirational. But I'm serious, it was great. Okay, so we, in general, yeah, it went from being like this to a little skinnier, I heard some people say. We are going to talk about whether we call this a compress or a stretch or things like that in a second. But in general, I'm going to call this a dilation, and you can use stretch or compress to be more specific. But it dilated. A way to remember that, anyone ever been to the eye doctor and gotten their eyes dilated?
Yeah.
What happens when you do that? Your pupil is right, moving. It's not shifting, it's moving in and out, and so it's kind of like this guy changing like this. So the origin, I'm still starting at the origin, but all of my points are just shrinking, compressing, kind of all those words. So we're going to talk about that as we move forward. Similarly, let's make sure we can then apply it. Yep.
So this one though, which one is this?
Which one is this? Okay, I was going to get into it in a second, but I'll talk about it. Since this 2 is on the outside, we're talking vertically about whether it was compressed or stretched. We're going to talk horizontal in a second, but this 2 is on the outside, so it's vertically doing something. If I took this parabola, did I take this parabola and stretch it, or did I take this parabola and compress it? Stretched it. Like I pulled it, and if I compress it, it'll flatten out, right? So I stretched it, and so this is a vertical stretch. But you'll see later, it acts kind of differently, stretch and compress, when we're going this way, horizontally. But because this is vertical, this is a vertical stretch, okay? Next, okay, that one, since it's also a 2 on the outside, should vertically stretch it up, and like you guys said, it should look skinnier as well. Okay, let's go to the inside. Look at the difference. 2 is on the outside, 2 is on the inside. Notice it still looks what?
The same.
Skinnier, right? It still looks the same. However, this time, Kennedy, if I want to take this and make it look like that, am I compressing or stretching? Let me try again. This picture, to get to this picture, sorry, I'll go over here. Did I compress it or stretch it?
Okay, so from the left to the right, right?
Yeah, this is the original. This is the one over here. Sorry, I should start over here. Did I compress it or did I stretch it to get to that? If I take it and I push these, they'll go. Yeah? Like here. Push my arms. Right? Do you see it? That literally works. Huh?
So wait, the parabola's function to change it, to stretch it is the same as the absolute.
Yeah. So this is a horizontal compress because the 2's on the inside, but when the 2 is on the outside, right? When the 2 is on the outside, because we're talking about pulling or pushing from the top and the bottom, that was a, like we said, vertical stretch. So the confusing part is stretch and compress. A lot of people like to think skinnier is always this one, but it depends on whether we're talking about the number being on the outside or the inside, because that's whether we're doing the stretch compress this way or the stretch or compress this way. Okay? But think, if it's on, we're going to do a lot of this, but try to stick with me with your brain. If it's on the outside, then we're talking vertically. So picture what would happen to my hands if you push my hands from the top and the bottom, or if you pull my hands from the top and the bottom. Okay? And think about if we're on horizontal, where it's on the inside. Now I'm not going from the top and the bottom, I'm going side to side. If you push my hands, it's going to do that. If you pull my hands, it's going to do that. Okay, so it's going to change depending on where we're compressing or stretching from. Okay, but we'll stick with that and see what happens. Okay, so let's go to our little box. I know, we're going to go to the box. We talked about, in our observations right there, kind of exploring, we looked at adding or subtracting on the inside, adding or subtracting on the outside, and then we, also talked about multiplying or dividing, dilating on the inside or outside. So we got 4 letters that we're going to use to represent those changes. Okay? First is A. And if you look up here at our function, I'm multiplying times A on the outside of my function. If I multiply times a number on the outside of my function, we just talked about that. That is a vertical dilation. That's going to change it this way, right here. Okay? Vertical dilation. Specifically, in terms of stretching and compressing, if it's a fraction, between 0 and 1, then it's going to compress it. And vertically, if you compress something, that's gonna make it look like, if you wanna translate it to this kind of wider, skinnier thing, if you like that, if I vertically go like this to my hands, they're gonna go like this and it's gonna become wider, right? Okay? If I stretch vertically, that's for numbers bigger than 1. If I've got my hands and vertically I stretch it, I'm gonna go like this and it's gonna look like skinnier. Okay? Is that how you're supposed to get it? B. B, in my example up here, is being multiplied on the inside of my function. Okay, so we also saw that. If the number is being multiplied on the inside, inside means horizontal things, and we're still talking about a dilation because it's multiplying, so we're talking about horizontally stretching it or compressing it. Okay? If B is a fraction, it's going to stretch it. If B is a number bigger than 1, it's going to compress it. So let's talk about that again. If we stretch horizontally, if I stretch these horizontally, I'm pulling from like my fingertips, I'm going to get wider. And if I compress, which means push my hands from the side, I'm going to get skinnier. Okay? Okay. H. Here's H. You'll see it up here. It's adding or subtracting on the inside. So that would be a translation or a shift. And if it's on the inside, that's going to be side to side horizontal translation. Either left or right, side to side. And if you subtract, it's going to go to the right. And if you add, we said it's going to go to the left, kind of the opposite of what you would think, right? Last one, K, is being added or subtracted from the outside. So that is now back to vertical because we're on the outside. And since it's added or subtracted, it's going to be a translation or a shift up or down. If it's added, we said it's going to go up. If it's subtracted, we said it's going to go down. Okay? Give you a second to jot things down. One last thing to note, this last column right here, everything we looked at so far was either like absolute value of x plus 2 or 2 times absolute value of x. There's just 1. But we could have both. You could have like 3 times the absolute value of x plus 2 off to the side. If you have multiple things going on, like a, b, h, and k, maybe you have all 4, maybe you have 2 or 3, then you got to kind of figure out which order to go in, and we'll talk about this more as we see more examples. But just for right now, you can just record the order that we're going to go in, and we'll kind of come back to talking about how to do that as we're shifting around and all over the place. Okay. All right, moving on. The only type of transformation that we haven't mentioned yet that I want to show you is also something you might have heard, a reflection. Have we reflected things? Okay, I see some nods. Okay. A reflection, if you notice here, I've got my square root of x. I reflected it. What changed about my function to reflect it? What did I add to the root x to reflect it, Lyra? A negative. Cool. I here added a negative inside, and here I added a negative on the outside. What's the difference between adding it inside and adding it outside? Nazra? Outside goes across the x. If your negative's inside, it gets reflected across the y. So you can just memorize that. Outside x, inside, press the Y. But I've never come up with a good way to remember that, and I literally always have to like stop and think about it. And you guys are trying to memorize a lot of stuff, like in this unit. So one way that helps me to think about it, oh, you got one, Kennedy? How do you think about it first?
So that one is like right next to the X, so the X likes it. It gets translated over the X axis.
Oh.
And then that one is outside, so it's like, I don't like you, go over the Y.
Oh, okay. I like that. So that's one way. If you like that, you go with that. I like it. We're into the memory tricks, okay? Another way, oh, you got one? Okay.
So, no.
Yeah.
So that one is Y?
It's across
Y.
the
I have one, I
Y.
have one, I have
Okay, go.
one. So you can make a Y out of that. So one line and then one line.
But what if it's not this function?
Ah!
But yeah, I like that for this. You could remember this one example and it could work. But then if it's another function, it might look kind of different. But I like that. You all are getting good at this. Started by Brian, all the memory tricks. Okay, one other way, if you're like, not feeling it, that maybe you'll like. Remember everything I've mentioned so far on the inside, like if I add 2 on the inside, that's things happening this way, right? Like going backwards or forwards. And so things on the inside still are going to move it from this side to this side, or if it was on this side to the other side. Okay, so side to side, if you want to think it more across Y is side to side. On the outside, if I added 2 on the outside, remember we said it would go up or down? So anything that happens on the outside, whether it's multiplied on the outside, whether it's added on the outside, all those things do things up and down vertically. So vertically, I flipped across the x-axis from the top to the bottom. So if you like inside, side to side, outside always up and down, that's another way to think about things. Cool? Or you say X, I don't like you going across the Y. Whatever, that whole thing. Cool? I like it. If it's on the inside, all things inside so far we've been saying are side to side, right? Outside is always up or down. Even with dilations. When we multiplied times 2 on the outside, we were talking about a vertical dilation. When we multiplied times 2 on the inside, we were talking about a horizontal dilation. So that way you can kind of blanket to everything. Brian?
You know, I kind of think the way that Kennedy thinks. If you have the paper and you like flip it this way, you can see that the square root is like the shield, so it's like protected. Just like that.
Full on story lines going here.
Okay, hold on.
How's the
Okay,
X feel?
this is the square root, right? And this is the negative.
Okay.
So if you rotate your paper this way, then it has this on the bottom, so it means it's going to go this way.
Nice.
This is
Good. I like it. Keep thinking of them. Hey, whatever works for you. I support it. Okay. So, with that being said, we are going to spend 6 minutes because we got 6 graphs right here. 6 minutes when I say go, taking the absolute value function. Everyone find the absolute value function on your foldable right now. Find it. What does it look like? This, we keep talking about. Find the absolute value function. You are taking this graph and you're going to be doing lots of things to it. All sorts of based off of what it tells you to do. So your task is to draw a sketch. Do not use your calculator for this because I don't want you to just see what it does. So calculators, don't do it. Don't calculate. I want you to think about where it should be moving or dilating, and I want you to draw a sketch of it, and then we can check on our calculator maybe in our last minute if you have extra time to see if you're right, okay? You may talk to your neighbors as you do this about these problems to discuss any questions you may have. 6 minutes on your mark, get set, go. No, I want you to do this. I love it, but I want to hear it later. Right now, you only have 6 minutes, you have a minute for each. So absolute value of x plus 2 on the outside means where's it going? Up 2. So just draw it up 2. Done. That one's done in like 20 seconds. Right? Absolute value of x. This one. If you add 2 on the outside, it's just going to move it up 2 and it's going to be up here. Alright. Very good. Kevin's off to a good start.
It's together.
This whole thing.
Okay, where's outside?
Yeah, which one? Are you on this one? This one? So this one is, we're talking about, it's inside, so we're talking left and right. But this is not a compression or a stretch. So it won't be going in or out, it's literally just gonna be this. And it's gonna be +3, which is the opposite of what you would think it would go back 3. Yeah. For this, first it's got a negative, so we talked about how negatives are gonna take us and, or, you know, like it's gonna rotate either way. If it's on the outside again,
So it's two.
we're still talking up or down, so it's gonna go down, okay? Then if it's 1/2, 1/2 is a fraction, and we talked about how fractions are going to widen it, and it's gonna go like this. So like if you, did you write my little wider skinnier? Notice here and here, see how they're both fractions? Both of them end up being wider. Whether it's a stretch or compress is like another story, but in terms of like drawing it and trying to see whether it's wider or skinnier, like fractions are gonna be wider, the whole numbers are gonna be skinnier. Okay?
It's 1/2, so it's going down one.
Okay. We're to the stretch, compress land, and all that. So first the negative. Okay, negative's on the outside. So again, think about your shield or whatever you're talking about. It's on the outside. Is it gonna go up and down, or is it gonna cross the X, or just one? It's gonna go the other way, right? Okay. Now the 1/2 is gonna change it
The
from
idea is that
either this
every,
to skinnier or fatter. It's gonna be fatter.
so every time we move 3 on the x-axis, it goes up 1 on the y.
Just remember, 1/2.
They're good. So you good stuff on the top. Now we're thinking about stretching and things on the bottom.
No, which one are you?
Okay. You're already in. Yeah.
You look like you.
Yeah. So this is still horizontal too, right? Like see how you move horizontally too? See how you move
Oh, yeah, okay.
And then this outside stuff is vertical, so you're up or down, and minus 1 means you're gonna go down. The thing with the horizontal is that what you're doing inside is opposite of what you feel like -2 means you're like forward 2, adding 2. On the outside, it's nice. Yeah, it's like what you would expect. It's like the -1 yeah, the bars are telling you like order of operations, like you've got to subtract the 2 before you can subtract, which is why it affects like where our graph ends up. So like you could plug in a number if you want, like 0, and before if you plug in 0, you got 0, and so if you would. Now if you plug in 0, it's gonna go -2, but then you take the other right plus
Or the eight?
because that's the inside is gonna be positive, right?
It's because there's no more flavor.
But it's also kind of common sense.
Yes. Means it's not gonna go like. Okay, oh no. Okay, because dilation is first, it's not gonna go up, down, or slide to the count, because we can't just pick things out, that's the sticky thing about it. Most lines all around the I like to remember fractions, usually to us,
No, he said it takes
as
off
wider,
if you get it.
and numbers are gonna make it always look sticky. The compress and stretch are gonna be kind of confusing, whether if you need to like identify it as a compress or a stretch. Something that's a little confusing, but like for purposes right now, if you see it as a fraction, you know it's gonna widen. Because think about it again, when you plug in a point, it's no longer gonna give you 1, now it's gonna give you a half times 1, which is a half, and so that point is gonna be like lower over here at a half. And if it's a 2, it's gonna be up here at 2. Okay? So for that bottom one, the fraction 1/2 is going to widen it. That's the negative reflected. 3 seconds.
Are we doing this right?
The top 3 all look lovely. Let's talk about dilating. Let's talk about multiplication. Okay. That's harder. Okay. Alright, y'all. Let's take a look and see what we got. I'm going to kind of cruise through these just to check. And we will continue to talk about dilating and compressing and stretching because I've noticed that's what most people are struggling with, so we'll keep rolling in some practice. But I want to make sure we get to all the examples before we get out of here. So first one, adding or subtracting, we're thinking we're in the land of translating, which we love because we just move around. We don't have to dilate. And so we are going to go up 2, and our graph should have looked like this. That's how most people have it, so I'm not going to talk about that much. Next one, plus 3 on the inside. We're thinking side to side, I should go back 3. The opposite of maybe what you would think, not forward 3, back 3. Last one, we're going forward 2, horizontally on the inside. On the outside, up or down, we're going down 1. So go forward 2, down 1, and your absolute value function will be over here. Cool, those 3, if you feel good about those, you're in a good spot. Now we're going to push ourselves to see if we feel okay about dilating with fractions and whole numbers and all that good stuff, okay? If I've got a negative 1/2 of the absolute value of x, in general, I saw a lot of people that they knew what to do with the negative. With the negative out front, if I had this originally, what's it going to look like now if I have a negative? Pretend the half's not there. It'll just, yeah, I saw Larry do it. Don't worry about the half right now. If it was negative, we just know in general it's going to be down now because it reflects across the x-axis. The way I said it was on the outside, think we're still up and down, and so it went from being up to now it's facing down. Okay? Okay, the 1/2 in this case is going to make it look wider. It's going to widen it up because it is a vertical compression. If you go back to your box, it says that if A was between 0 and 1, it would vertically compress it and make it look wider. Okay? Next one should be not moved anywhere, but look like, I guess, skinnier. But that is a horizontal, because it's on the inside, horizontal compression. And last one, we've got a horizontal stretch, making it look wider. And then the plus 1, we like that. Where does that go? Up 1. Yeah, you like have it. Up 1. So it should be wider and then up 1. Okay? Okay. Last 2 that will look similar to like something that you're going to see on your problem set. Okay? If you take a look at these 2 graphs right here, this first one and this second one, both are coming from the parent function, the quadratic x squared, right? Okay. I want you to verbally, using these vocab words, describe to me what's happening, and then we're going to use that to write our equation. Okay, so we'll do the first one together, then you'll quickly do this one. Taking a look at this, if this is our original quadratic, who can describe to me using our vocab words what happened? Or if not, you can just try to use your own words. What happened? D'Anthea, try it out.
It's negative. It went up 2.
Okay, so let's talk description. We'll get to like the negatives and what happens here. But it went up 2. I'm going to call that a translation or a shift up 2. Okay? So use whatever word you like, but translate up 2 or shift up 2 or move up 2. And then she said something about a negative. So when we're talking about negatives, that was a reflection. Good. Reflection over the, since it went up and down, it's over the x-axis. Okay? So now, D'Anthea already said the reflection is going to come in with a negative. Okay? How am I going to, Martin, how am I going to translate up to? What do I need to do to the x squared to translate it up to? up 2 means what am I gonna do in my equation?
Plus.
Plus 2. And I do it on the outside, move it up or down. This would have moved it left or right. And then I have my negative out in front to flip it, right? Okay. Next up, this guy. Go ahead and with your neighbor or by yourself, whatever you would like, I'll let you choose. Write your description and try to come up with your equation for this one, okay? Go for it. Oh, gotcha. So this, all of them are different functions. So all of these were coming from this graph. We just took in and we changed things. This graph doesn't look like square, right? It looks like this one, the quadratic, which is x squared. So we're doing things to x squared. We were doing that one earlier. So like later, you could also be doing this one. Like it could be x cubed and you could add 2 and it would shift that graph up too. Cool. So you gotta identify the parent function, and then you gotta change it.
With this one, I think it's, first of all, you have to find the parent function too. Like say absolute.
Yeah, because it went up and down. But then this time, if you wanna go right 3,
So
that's
for
gonna
that one, I
be
think there's
minus 3. Oh, I think it's actually between 2 and 3, it's like 2.5. And you would have to do that underneath the square.
one that's a vertical stretch.
Like in the parentheses.
Huh?
Okay, for this one,
No, I'm talking about
let's
this
talk about it in our last minute so I can let you out on time. Who can tell me what happened without the equation yet, just what happened, Kevin?
Right, 3, reflection will be excess 3.
Okay, right 3, and one more time, use one of these words. Was it translation or dilation? If we're moving right 3, is it dilating or is it just translating? Translating. So translate or shift. Either of those works, okay? Right 3, and then it reflected across x axis. Listen up. So we end up with the x minus, oh sorry, not 3, it actually was 2.5. Yeah. 2.5. I was like, yeah, Kevin. 2.5 squared. So it's on the inside to move it right. And then we've got our negative out front to shift it, or not sorry, shift, reflect it down across the x. Okay? Bye-bye. Earlier, all of these we're taking it here. Later, you can be like, See you later. Oh, good.
Hey, bro, not bro. Oh my God.
I actually